So this talk is definitely like technically oriented, but I'm going to stay as far away from specific technology things as I can. So you've seen the Kafka logo there that hopefully tells you something, but I'm not talking about Kafka, I'm not talking about Kinesis, I'm not talking about any particular streaming technology. I'm much more interested in the architectures of where I think we're going, actually. So I've only got 45 minutes, and in those 45 minutes, I can't really break us all down and like rebuild us thinking about streams. So, and I've got lots of stuff to get through, so I'm going to kind of fly. There might be a whole ton of details that get missed, and that's okay. And hopefully, my idea is to try and seed at least some ideas with you guys to go and have a look at maybe some other things or think about stuff differently. Otherwise, you can come and grab me or some of my colleagues, like in the expo hall or over beer or whatever it is. Okay, so first, who am I? My name is Tom. I work for an awesome company called Synthesis. My official title is Chief Disruption Officer, and that means I get to play with stuff that makes people feel uncomfortable sometimes. So I quite often find myself in technical conversations with groups of people who go like, what the hell are you trying to tell us about this stuff, right? So quite often, yeah, I run a lab at Synthesis where we evaluate particular emerging technologies and determine whether we should bet on them as a company, if this is something that we think we should be sort of placing the next 5 years worth of skill and capability on. We bet on AWS about 6 years ago, and I think that's been pretty good. We like the exciting and disruptive ones because what that means is that there's this kind of skills, there's going to be this pending skills shortage in that technology, you know, within our customers, within the industry, within communities, etc. And we can try to get in there a little bit earlier, right? And try and like maybe try and seed some of that skill. It's super cool to be presenting at DEVCon. I've actually never attended DEVCon, so here I am for the first time and standing in front of all of you guys. It's pretty scary. So I thought I'd start with a tiny bit of my personal programming background. So I definitely call myself a functional programmer. However, I've worked across a bunch of different languages and platforms, and although my preference tends to be to choose languages that promote a more functional style, I'm also like a happy camper in most OO languages. And that's probably mostly because OO languages, I think, are becoming more functional. Don't tell them, but that's a good thing, right? So I like lots of languages, and also sort of in the last 2 years, I've focused quite a lot on hyperscale distributed platforms. All right, so let's talk very briefly about functional programming. Actually, I didn't realize that was there. And check out this. I've got a mobile device that I thought would be awesome for the first time to present, and like check, there's like 4 adapters that I have to hold on to, so not really working out, but I'm going to go with it. So my first job in 2001, don't work out my age, was with a military company called African Defense Systems. I worked in a team of about 20 software engineers on a project for a period of about 3 years. We literally wrote millions of lines of procedural C code. That's what we did across about 40 different subsystems. So within the military, we talk about things like subsystems, about 40 different subsystems, controlling different functions of a military battleship. So if you've ever been to Simonstown, you would have seen the 4 big battleships there. I worked on that project. I was super lucky because over that period I got to work with some seriously talented programming gurus, some of which became my mentors during that period. And so even though I'd studied computer science, I learned literally everything with that team. So threading, pointers, memory management, debugging, 8286 assembly, TCP/IP, multicasting. We generally built our server side running on Linux, sort of launched by initd, and our front ends, which we used to call MMIs, man-machine interfaces, were generally written using Qt and running on X Windows. So although we had millions of lines of code, and it was all very procedural, it was super simple. The code was really easy to understand. It literally, like there was no abstraction. Stuff was super simple. And it was really easy to detect memory leaks. It was really easy to detect wild pointers. We used tools like Valgrind. So I left that company 2004 or so and joined Synthesis. And I took it upon myself to become an object-oriented guy. So at Synthesis, object orientation was a big deal. I kind of knew a little bit of it, not a ton. And so over the next sort of 7 to 8 years, poured myself into object orientation. Wrote thousands of lines of polymorphic stuff. I hid lots of concrete implementations behind interfaces, inherited, encapsulated, abstract base classes, the whole thing. I was totally convinced by it. But it didn't bring any simplicity whatsoever. In fact, exactly the opposite. Stuff was harder to debug. It was less obvious to understand. In some cases, it was like far less performant, and it was really hard to figure that stuff out. But it didn't really matter because we'd all bought into OO, and that was like the ideology, and it was the only thing we knew how to do. But probably around 2011, I started looking more seriously at JavaScript and Node.js back then. Back then, it was Google's V8 JavaScript engine ported basically to the server side. And I remember reading a blog post about Node's ability to serve literally millions of concurrent web requests per second from a single process. And that kind of blew my mind at the time. Back then, my world was sort of threaded, etc. And so this like millions of concurrent requests served by like this toy language called JavaScript was like, I couldn't understand it. And it would outperform stuff like Apache HTTPD, which was written in C and C++. But it was enough back then to convince me that it was worth getting into. And so I started my journey, sort of relearning almost everything. Along the way, getting into the asynchronous programming model, event-driven, single-threaded, like going back to single threads, guys. This is like the kind of the answer, actually. And that was my gateway into writing functional code. My code since then, I hope, I don't know, has become like simple again, actually. Completely straightforward, not hidden behind weird abstractions and patterns. It was like right there. So I've summarized, I think, 3 good things about functional programming. Number 1, immutability is good, and like you kind of can't deny it for a couple of reasons. You can parallelize stuff. It's really easy to test. Code becomes portable, like copy-pasta type code is really easy when it's all based on immutable concepts. And you generally produce way less bugs, and like anecdotally, I suppose. Other good stuff about programming, functional programming, is that you start to solve problems using data structure and the mutation of that data structure over time, and kind of focus less on the structure of my code and the logic and how I structure logic within something weird like an object model. And then the last thing is composition. And composition I'm going to speak a bit about later, and I think actually some other speakers have also. Composition's been a bit of a theme. So some of the like not so important stuff about functional programming. So like definitely if you decide to get into into functional programming, go and read a book called Learn You a Haskell for Great Good. You can just Google it, and you'll learn a bunch of like awesome sort of pseudo-mathematical, pseudo-philosophical theory, and that stuff is really cool, and you must definitely go and do it, and it's super fun to read, but it's like fairly useless, some of the advanced concepts for like a real developer, right, who needs to produce working lines of code every day or whatever. But in your spare time, absolutely worth it. So these things, and I've kind of listed sort of the sort of things that are, they're kind of focused on Haskell as well. A lot of these things bleed into other languages, and I think when they start to bleed into other languages, they become a bit more practical. Like Haskell's a great language. I've never written anything meaningful in it, but like super fun, right? So some of the stuff like that's interesting: monads, functors, monoids, applicatives, category theory, like brilliant. It will teach you very little about writing like the next, thing, feature that your Scrum Master needs you to build. But you'll have good conversations with people around the water cooler, and you'll spend maybe hours in front of a whiteboard with, who knows. And so again, sort of focus on these 2 things, like what data do I have, and what transformations do I want to do upon it, to solve my problem, actually. And those 2 things actually work really well in just sort of breaking your problem down into manageable steps. So I have no live code, but look, I wrote some code. This is DEVconf, right? So let's talk really quickly about immutability in a kind of dumb example, but I think it's pretty cool. So we've got this code. I'm not sure what language it's in, but it doesn't really matter. So we start with an array. It's called names, and it's got 4 names in it, a sort of list of strings, right? We're obviously, I think if you read through it in detail, we're trying to find all the names that start with T. And so sort of naively, we go names starting with T, starts out as being a sort of empty array or list, and then we iterate, right? So for name and names, if that name starts with a T, then append that name to name starting with T, right? And then we print it at the end. So like, what's the problem with this code? And fundamentally, like, that's the problem, right? It totally lies to us, actually. So when we read this code as, post fact, we go, oh, name starting with T is an empty array, right? And it's like, well, not really, is it? I mean, maybe at some stages of the program it's an empty array, but like, depending on when you ask me, this thing may have Tom in it, or it may, a little bit later, have Ted in it. And so, like, code that sort of presents lies to us like this is something we should try to avoid. So another downside of this kind of thing is that this code is really hard to reuse because it's kind of made up by like a bunch of different units, right? We start with, we've got all this dependency between this. We've got this for loop that's like totally dependent on names starting with T. And within the for loop, there's an if thing, and it's also dependent on that name starting with T. So we can't really just like grab out little lines of useful code here because like we can't really clearly see the dependency between them, right? These units are here, they're dependent, but it's not that clear. It's kind of too much cognitive burden, and even in this like stupid example. So what's a better way to do this? And like, I know we're all developers and we know this stuff. I'm not teaching you how to do it, but I'm trying to sort of create an example, right? So a better way to do it is this, right? We've still got our names equal, starts with the array of 4 strings, and now name starting with T actually is that same list filtered, but where the name starts with T, right? So I think I highlighted it. So like, there's no lies here, right? So either name starting with T doesn't exist because it's not in scope, and so like our compiler would be aware of it. Otherwise, when it does exist, it's absolutely a filtered list of names that start with T. There's kind of no other little funny sub-state, right? And so here, there's only really 3 lines of code, I suppose, in our program. They're all kind of copy-pasteable, right? I can steal them all, and I kind of uniquely, they're all kind of bound together. Their dependencies are together. Okay, so enough about this stuff. And the point is that you should use this stuff. It'll make your code better, I'll guarantee you. Also, this sort of thinking can eradicate null everywhere. And I'm really excited to see that popping up in other languages. So good functional languages have no concept of null. I mean, it's not like, I'm not going to get into it. Get rid of null, like you don't want it. You don't want your stuff to have this other state that it could be in that will break stuff, right? It must be in a known state. Okay, so let's talk about interesting stuff. And in this talk, I'd like to challenge 2 things that we generally take for granted in software architecture. So the first one being stateless. Like, I think everything in architecture today is stateless. And number 2 is this concept of a request and response, right? They're like so ubiquitous, actually, that we probably don't even know that we're using them. And I think most of the time, these are the only tools that we ever consider in our architecture toolbox when we design stuff. Okay, so right at the end, like use streams. So my discovery of streaming architecture, I sort of opened my eyes to streaming architecture when I started to question those earlier 2 things. Streams, however, bring such a foreign set of concepts, and I think often that people try to build bridges from their comfort zone. So when you think about your current architecture today and you go, oh, the streams thing, like maybe I can just append it on somewhere, that's a bridge, right? I'm trying to like figure out like how it's compatible with my architecture. I think fundamentally with streams, it challenges stateless in a way to say actually stateless should become stateful, you know what I mean? And it's like really hard to build 2 bridges between these worlds. And so quite often people fall into the trap of saying, oh, streams are just queues, right? It's just a way of messaging stuff. It's just another form of request response between 2 stateless systems, maybe. But streams are not this, and it's an error to think about them that way. And in fact, are much worse than queues when you use them like queues, so don't do that. So we'll talk a bunch about streams, but basically it's fundamentally an immutable commit log, whatever that means, we'll talk about that, and I explain that. But also it's fundamentally a distributed data structure, meaning that it's a great core component when you're wanting to do stuff at scale. And it's got nothing to do with Netflix or Showmax, that's another thing. I talk about streams, people often say, yeah, but we've got no media, like stuff, we're not trying to stream things to people. Like, no, it's not really what I meant. Okay, so here's a bit of a thought experiment. So if we imagine that this SQL statement at the top, update name set status equals active where name equals Tom, instead of that direct, so we know what that'll do, right? It gets written to, it hits a database, and the database just modifies or mutates that row, right, and updates the status to active. So let's imagine that instead of it directly modifying that table, it simply just appended a record to a never-ending log of updates to that table instead. If what we wanted was still a table where we saw the mutated records, we could do that, right? We've got this commit log. We can always, it's called materialize it. We could materialize that thing, reduce it, and merge that to the latest entry, and we could create that sort of table on the right, which is what like our original database would have done, right? However, we can also do other stuff. For example, if we wanted to, and this is really silly, but like if we wanted to get a list of ages grouped by each name in the log, we could also do that and produce another kind of table structure based on that same commit log, right? So the point is that fundamentally an immutable commit log structure, with an immutable commit log structure, we can produce something that looks a whole lot like what we're used to in the database world, but retain all the benefits of immutability that we talked about before, right? So this is immutable. We're just appending to the end of it. Another nice benefit is that because we keep the rawest form of the update, we maintain the concept of time within our structure, and as such we can derive other future structures from it, for example, that second attempt. And in fact, sort of in a year's time, we could run another little thing and produce another piece of data based off of that same commit log. Yeah. So where does this lead us? And to all of those people who are not familiar with streams, it's a pretty scary place. We generally think about services being stateless, and their primary role being to broker updates and queries into some kind of mutable data store, right? So at the top, stateless services, they generally mutate some database at the back by updating it, and when they need stuff, they'll query it, right? Streams take us to a place where our services become more stateful, actually. And instead of updating a store, they simply append records to an immutable commit log, where either they themselves or others will consume those same records, updating their own internal states. So if this sounds crazy, stick with me. Who thinks this sounds crazy, actually? Put up your hands. There's one, two. Only two? No, rubbish. Mike. Sean, thank you. It's like everyone I know, basically. Thanks, guys. Shot for coming. Okay, so let's take a quick trip through my version of a history of architecture, right? Architecture 1.0, user hits a system, that system stores stuff in a database, we got it, right? Then we learned about services-oriented architecture, and we said, actually, we need to split that system thing into maybe different parts. There's probably a back-end part and there's a front-end part, because I think in SOA, in the early days of SOA, we realized that actually there's no longer a one-to-one relationship between front-ends and back-ends, and maybe it's more many-to-many, right? We want services to call other services. Many front-ends might call that same service. That service could be, etc., right? And so we split these two things, front-ends and back-ends. Back-ends holding like business logic abstractions, front-ends holding presentation logic abstractions. So this was good and worked well, but it was still monolithic and didn't scale, right? So architecture 3.0 came along, and like maybe not that long ago, actually, 2010 was my guess. Well, that's when it came into my brain. And so suddenly we had businesses that needed to reach millions of customers, right? And traditional SOA didn't work, so we invented microservices. Smaller services, very specific functionality in each one, able to deal with unpredictable load from a customer base. presented a ton of interesting new challenges when you dug into it, and a whole lot of cool technology popped out that made this pattern easier to build. So stuff like Kubernetes, the Netflix OSS stack, all these kinds of things came out because it was like hard to manage a whole lot of different services. And problems like service discovery, service meshes, load balancing, circuit breakers, all jumped in there. And we're probably mostly still in that world. This is the only meme, I think, in my presentation. So I think we realized quite quickly that breaking up the stateless parts of our system didn't get us all the way there. We also had to break up the storage layers, actually. And we'd maybe just move the bottleneck sort of one layer. So we invented the concept of bounded contexts to separate out each persistence layer for each microservice, meaning once again that each data layer could be scaled independently again. Including its data piece, and it also allowed us to maybe reduce some of the blast radius when stuff went down, etc. So as part of this journey, the sort of RESTful microservices one, there were a couple of rules we had to come up with. Things like service A must talk to database A for its stuff. It mustn't reach across and talk to some other guy's database. It should rather talk to that service via its contract. And this presented like a couple of interesting problems that weren't that obvious to sort of encode as rules, right? The trouble kind of comes when you realize, so service A is calling service B, and that's a good thing. We said that's good. The trouble comes when we say, well, service B also talks to service C, and potentially service C talks to D and E and F and G down the line. And then we kind of, it was hard to solve this. And so I think a lot of people said, well, yeah, we like service A talking to service B, and service B talking to service C, like we like that, okay, but not too much more of that, right? That's sort of how we dealt with it. Then some smarter people said, well, actually, maybe we need to encode this as a rule, as a pattern, because it doesn't scale. Not so much is not a good rule. And so kind of split the world, and this is just one idea of splitting our microservices into kind of different virtual or logical layers. So number one, having foundational services, and they're allowed to talk to databases directly, but not to anyone else. Orchestrational then layers can speak to other orchestrational services, so that's cool, and they can speak to foundational services, but they can't have a database. And that way we kind of said, yeah, okay, this already sort of limits us at least to, maybe at most we're going to see kind of 20 requests deep in this kind of thing. And so like maybe that's a good kind of band-aid, but I'm not convinced that it's general enough to suit all problems. Other issues were things like transactional issues where, in architecture 2.0 world, we could say begin transaction, update, commit, and like all of those things were done. When we had the monolith, we could completely have integrity in our databases. As we split those functions up and we put them in different services, transactions, I think we just forgot. I think we just said, yeah, like that's just like we kind of just can't have that anymore. And I think we said, yeah, I think that's okay. Maybe it's okay. I don't know. So service A, is trying to do two things. He's trying to make two changes, maybe because he's an orchestrational type of service where he would have to be in this diagram. He asks service B to do something. Service B goes, cool, I'm done. And then service C goes, like, nothing. You get no reply from service C. So, like, where does that leave you, right? Another issue is this sort of compound blocking, I call it compound blocking issue, where service B being a complete dependency on service A, or service A having dependency on service B, means that like it's very hard to now isolate the performance of service A. If everything he does relies on service B doing something, he can't be any faster than the slowest service B, the fastest service B can be, right? So it's kind of hard to separate these two things in the request response world. And so quite often when you have this situation, you then introduce asynchronous messaging between these two things to then try and decouple that sort of performance binding together. And that just brings like another level of complexity, right? And then the last one I call getsplosion. And this is where, and this I think is actually just a characteristic of stateless design. Like, none of these services hold any state, right? So when we need to get state, we have to go and ask them for it. They have to ask downstream. They have to get it out of the database or whatever it is, and they have to rehydrate all the time. And so, and mostly I think that's fine, but there are a few times in our system, for example, when I log on to an app for the first time and my front end has got zilch state, it needs to get all of it, right? It needs to get all the state for Tom. And so that can turn into, potentially, 80 service calls to the back end to go fetch Tom's accounts, fetches balances, fetches, whatever that system does. And those all things, trigger gets throughout the entire system. And I think maybe suboptimal, I don't know. So when I think about some of these issues in microservices, it's kind of hard to pin down what is the root cause here? What is the root issue actually? And so maybe we're looking at the wrong place. I think we always look at the little boxes and we say, well, how could we structure them differently to get boxes that don't have these issues? And maybe the problem sits between those boxes. Maybe it's this request response thingy. And maybe we need to look at that, right? So maybe PubSub is better. Some people may call these queues or asynchronous messaging. Does PubSub solve all of our problems? So, well, let's have a quick look. So PubSub is super easy to understand. One party sends a subscription request to another party, and from there on, party B will send party A updates whenever that thing changes, right? But there's a few problems with this. So what about the initial state? So if A knows nothing about what's ever happened in B, he now subscribes to users. How do I get the starting set of users, right? And did that subscription request in the beginning mean give me all the users also at the beginning? And I'm not sure. So I'm not a PubSub expert, but when I look at this, I go, yeah, I don't know. I still think I would be subscribing to users and then probably along the side, probably doing a GET request to go and get all users as well. And so I'm not sure if I'm solving stuff. But so let's look a little bit further. So when PubSub services perform an update, it would generally update its data store through to the database and then publish the changes to all subscribers, right? Couldn't we leverage the database somehow to keep track of these publishable updates? Meaning that subscribers could choose themselves to which events they'd like to consume. Don't databases already have a commit log? I kind of remember in my university course, we spoke about commit logs inside databases, right? So let's have a look at that quickly. So good databases actually do support the notion of a commit log already, but they really only use it for internal purposes. So there is an internal commit log, and what that means is when I go begin transaction against a good database, it would create a commit log for this transaction. So any updates, I then go update Tom, update whatever, those all go into a commit log. They don't yet get committed, I suppose, or written down to the tables, because it's possible that I roll it back or that I do nothing, and at some point that commit log either must get truncated and written down to disk or be thrown away, right? Yeah. So those two concepts are super awesome. And as we've seen, both the commit log and the compacted tables have value to us, actually. We can see two good use cases there. It's kind of really a pity that the database throws the commit log away. So what if we simply dropped the database part and made those two structures available directly to our services, right? And in fact, make the requirement of having to compact and truncate just the responsibility of our service, actually. So our service could choose to do stuff either directly against the commit log, or it could do stuff, it could respond to queries potentially through actual reading of materialized tables and indexes. And this is kind of fundamentally the idea of streaming microservices. Well, my view of it, I don't know. So let's talk about database classes quickly and some theory we might have forgotten. So typically, you split the world into these two concepts, OLTP and OLAP. And if you've forgotten this, it's totally cool. I totally forgot about it as well. And unfortunately, and it's because traditional databases, RDBMSs, are very good at both. We've actually never really had to realize that we have two different modes of interaction with a database. The one is highly transactional, so that means it's stuff that my system is intended to do, right? If it's an online banking system, it should make payments, it should update, it should be able to fetch statements, etc. It should do all the functional parts of my system. And that's the OLTP side of my world. OLAP is more the analytics side. So that means being able to run ad hoc slice and dice type queries across my data store. And databases, traditional databases, are really good at both. And so we've kind of conflated these two things. So I think, so when I think about these two interaction classes, I feel there's a bit more of a slant towards the commit log with OLTP and a bit more of a slant towards tables and indexes with OLAP. And it's not universally true, because in the OLTP world, we still also need some kind of tables and indexes type of view, but in the transactional sense. So stuff like, what is the balance of my account? I probably wouldn't want to run through my commit log for all time to figure that out. I could probably just materialize that into a table, but it's still on the OLTP side of my world. So streaming is an OLTP thing, because it uses the commit log at its core. And stuff like data lakes or traditional databases complement streaming by playing the OLAP part of our system. That's kind of how I separate those two worlds. So that was an interesting journey down PubSub, right? Is there anything else? What about this thing? An event. So what about events? So I wasn't sure how to draw these things. So this looks like a sea urchin or something. I don't know. Like, I'm open to ideas, guys. What does an event look like when you draw it? I'm not sure. But the coolest thing about events is that they just appear, and they really have no directionality to them, which is super awesome. Like, there's no dominant entity when in an events world. So like, when we think about request response, we always, like Jerry's talk, she had the sender and the receiver, right? Like, we always, it's very clear in a request response world who's playing what part of this conversation. When you get into the events world, you've got to drop that stuff. Like, events can be emitted by anyone, and they can be consumed by anyone, right? And it's no longer important who initiated it, who consumed it. There's no request to responder. The other cool thing I thought about, and I haven't thought about it enough, but I think events are also composable. So if I think about it, I could have two events. One is an event which is generated when something becomes active, like anything becomes active. That's an event. So I could say, hey, like, I'm interested in all events about anything that becomes active. And then I could have another type of event, which is like, hey, I'm interested in changes to orders, right, in my system. And I could take these two things and compose them. And now suddenly I have a third event, which is whenever orders become active. Do you know what I mean? I've composed these two things, which I think is interesting. I'm not sure. I mean, maybe you want to argue with me. I don't know. And I don't think you can't compose request and response, and you can't really compose PubSub either. Okay, so I said streams a bunch, right? And we sort of know it's a commit log thing, but this is what it looks like conceptually. So this is my own notation. I use little angle brackets that represents a stream. A stream contains a set of records, and a record is that thing on the bottom left, key equals value. And producers, when they write to a stream, they write to the head of the stream into those three dots space there, and you can have different kinds of consumers against a stream. So it's not a queue, because a queue can't really have many consumers at different offsets along a stream, right? It's like a queue, except the records don't disappear, and you can be at a different point in that queue as I'm consuming through it, right? The last cool thing about stream, or most general stream technology, can be very type aware. So each record on that stream can be well typed, and but they don't necessarily all have to conform to the same type. So we could have a stream containing multiple types of records on it. The most interesting part is that it could be the same type, but it changes over time, if that makes sense. So you can think about a single stream holding records for the first year where we used version 1 of what a user looked like, and maybe we deployed something which changed the type or the schema of that record, and from now on we produce this sort of version 2 type. The stream itself still retains the version 1 types as well as the version 2 types going forward, which a traditional database can't really do, right? You can't have, unless you have two tables. I'm not sure. So physically, so that was the conceptual view of what does a stream look like. Physically, we know it's a distributed data structure. And a stream is actually composed of a number of different underlying partitions, which are responsible to do the actual data storage of records. Those are called partitions. It's the thing on the right. So keep in mind this thing is a distributed thing, so it needs to do this kind of work. So although we consume records at a stream level, there are certain properties that are only available to us at the partition level. So stuff like ordering is only guaranteed at the partition level. It's not guaranteed at the stream level. And things like locality. So if I'm trying to say, hey, like I want to calculate the balance for Tom's account, like it's going to be hard to do if all Tom's transactions are distributed across all these partitions. I need a mechanism somehow to get them into a single partition so that I can do that work. But this ability to consume records and repartition them is really powerful and really one of the fundamental strengths of streaming over other forms of distributed data stores, I believe. Okay, so what does a stream processor look like? This is now where we start to write apps that use consume and produce two streams. So at an atomic level, a stream processor looks like this. It consumes records from one or more streams on the left as a consumer, and it produces records to a stream on the right, typically. There's a couple of guidelines around building stream processors, and there's two good rules. The first one is a stream processor should never write to more than one stream based on a single consume event, and that's in order to keep transactional integrity. But if you don't care about it, then it's fine, break that rule. And secondly, it's generally a good idea to make sure that your writes are idempotent. So when you write them to your output stream, it should be okay for upstream consumers to be able to tolerate duplicates. And that's that's kind of like a low-level requirement. It's good habit. Some stream technologies themselves will deal with that for you. So Kafka, for example, has the ability to have, I think they call it exactly once semantic, where it doesn't really matter. So it's fine. You can be guaranteed to not have duplicates. It's just there's a small performance cost. Okay, so here's some code. So this is so we saw what it looks like as a block diagram. What does it actually look like as code? And really, it is kind of this simple. Like a stream process is really simple to write up, and it's really just like a combination of functional transformations of stuff off of that stream. So I think this is a really dumb example, but it should give you enough of an idea. So I think what it's trying to do is we're trying to read orders that are pending off of a pending orders stream, right? So we open that stream, it's called orders, and we filter it where their status is pending. That produces us a new stream called pending orders, right? Which is a variable. It's not committed back to the stream, it's kind of just in memory. Down below in the next line, we say, take now the payment stream, join that against the pending orders stream. And in this example, I show how the join occurs. So the orders ID has got to match the payments ID. That probably isn't how you would do it. Then we want to map that back to just get us back the single order and then pass that over to the completed orders stream. So like with this tiny little piece of code, we've been able to match a payment to a pending order and then turn it into a completed order. Probably somewhere in here we should have set the status to not pending. So there's a bug. So the previous example did that simple task, and that's probably one tiny little aspect of like the orders service, right? If I'm writing the orders microservice. And so it's important to realize that stream processes themselves are composable, meaning that, that could be that very sort of silly pending thing was maybe the top left, but the orders service as itself is probably a collection or composition of many stream processes together that we might now call the orders service, right? And the interesting thing is that each individual stream processor, not the outer service, is independently scalable. So if just that little pending piece was an expensive routine or whatever it was, we could scale it independently within the orders service. So which I think is a pretty cool level of granularity. Sorry, I'm getting emails. So here's like maybe just a more worked out example of saying, well, maybe there's 4 services. I think I've got a stock service, which is on the, I wish I could point, the sort of green one, which is just a stream of all of our available stock. Bottom left, we've got this like warehousing or dispatching service. The big red thing in the middle is like our order service, and on the right we've got our payment service. And they can all kind of interact with each other through streams. and we can kind of redraw it like this, right? So after composition, we can redraw it, and each service, payments, orders, stock, dispatch, each consuming off of one or more streams and producing to one or more streams, output states. And we could even call these microservices if we wanted to. Okay, so we talked about architecture 1, 2, and 3. So let's talk about architecture 4.0. So microservices was sort of the ideal form of architecture 3.0, right? But I believe architecture 4.0 will be primarily made of event-based streaming microservices. So I asked 5 different groups of people at Synthesis how they would describe streaming. And this was from Sasha. Sasha here, put up your hand. There he is. This is his fault. So he said to me, like, streams are super cool, right? It's like in an organization, data just moves around and like washes around like in a washing machine. The events are firing and other events then fire. External events come in somehow, and then we generate events. And so that's how one way of thinking about streaming, right? As in an architectural way. Then we said, well, if we've got one washing machine, we could have like a washing machine of washing machines, right? These things could talk to each other, and we could have little individually spinning washing machines communicating with events. And like, absolutely, like, how cool is that? I spoke to our data science team, like, what is streaming? And they're like, it's totally a neural network, right? Events come into the input layer, those neurons fire or don't fire, and up they go, like through all the hidden layers, and eventually you get an output. And that's what streaming architecture is all about. They even said, like, it's brilliant because you can even do recurrent, like, neural network sort of types of designs in it. I was like, okay, interesting, cool view. Then I spoke to Murray, who's a bit of a quantum scientist kind of guy, and he's like, streaming is totally a graph database. Records come in on one side, we break them out into like different like substates or whatever it is, and later on we can compose them back together. And then he's like, but the most interesting thing is there's this duality of queues and data stores, which he's a quantum guy, so I don't know. Duality of waves and particles or something came into it. I couldn't capture it well enough. Then I spoke to Paul. Where's Paul? There he is. So Paul's a Ethereum blockchain guy. And he says that like streaming is totally a smart contract, right? You've got this immutable ledger on one side. You're going to read, your smart contract's going to read that stuff, and it's going to write to some other immutable ledger. And it's absolutely just like the Ethereum virtual machine. And then I spoke to Chart, and Chart is, he works on my emerging technology team, and he's closer to building front ends and engaging with customers and building experience. And actually this one, shout out to Mike Geyser, I'm not sure your surname. You can put your hand up. He helped us build this actually, which is pretty cool. So streams, maybe it's this symmetrical thing where events can be fired on front ends, back ends. It doesn't really matter, but as long as we can connect our back end to our front ends through these kind of like distributed event stores, we can really start to see things as being like quite flat actually. Like just generate an event. Does it really matter if it came from the back end or it came from the front end? It doesn't really matter. We just see the world as this like flat list of events with publishers and subscribers connected, which I thought was pretty cool, creating this symmetrical kind of view. So it's really awesome to hear like 5 different views of what streaming architecture maybe looks like. And they're all built on this single fundamental building block. I think that's super exciting. So let's talk very briefly about the front end. I think I've got 5 minutes. I hope. So we said this. So this is charts architecture, the symmetrical one, right? We've got this front end, sends events to a back end. The back end generates events. And there's no kind of, it's not like there's an initiator and a responder in this thing. They're completely flat. So how do we do this? Most web frameworks today already support this like two-way data binding between a view and a state. So like Angular or React or whatever already has this. To enable an event model here, it's just simply a matter of sticking an event store before that state, right? So if you've got your view, that view is data bound to state, just sort of wire in an event store behind that thing, which will then just materialize that state. And So something, if anyone's used Redux, this is what Redux does, right? It just, instead of you directly manipulating your state store, rather generate some kind of event, and that event will reduce into your state store. Now the point is just to wire that thing up to your backend, right? So what about OLAP? OLAP is super easy if you want to do the analytical part against streams. It's just literally find the streams that you're interested in and just blast them, fire hose them into either your data lake or into your databases in real time. So as things appear on a stream, it can be materialized into a data lake where it's available for analysts or whoever, or to query those things. The same way that we've always done it. The cool thing is we can drop the concept of ETL here, so we can fire hose in real time. Okay, so let's put it all together. We've got this front end generating events into an OLTP backend that's materialized down into OLAP stores, and we've got some kind of BI front end ad hoc querying that OLAP store. But we're missing that AI thing, right? Because we have to talk about AI and predictive models. So like, where do they fit? Right there. It's like super simple. Predictive models are trained off of those OLAP stores, and they're wired in for inference as stream processes, actually, into our OLTP backend. And that, I think, is quite an interesting one. I think a lot of people struggle with, I think they're either very good at training models or very good at deploying models, and never really both, right? So a lot of customers speak to us about, like, we've trained this thing, and we just, like, what do we do with it now? It, like, runs on this guy's laptop, and now what? And a lot of the time we say, well, do that, like, wire it into some kind of streaming thing, and that way it's very easy to wire your models in. And so that's it, guys. That's architecture 4.0. So how do you learn more? It's really simple. Spend more time with the technologies that currently implement streaming: Kafka, Kinesis, Akka, Spark. But focus on the streaming parts, not so much on the queuing parts, because they do those pretty badly. There's a video by Martin Kleppmann. He's one of the authors of Apache Kafka. He works for Confluent at the moment, but he's got a great video, and it's all the way back in 2015, which is like years ago, called Turning the Database Inside Out. It's definitely worth watching that. More recently, there was a series of blog articles written by this guy, Neil Avery, also with Confluent, called The Journey to Event Driven. It's absolutely worth reading. And for web-focused people, like, use Redux. It works well probably with whatever you use today. And then for a quick note, come and visit us at our stand. We're in the hall there. And get in contact via one of these methods. Thank you all very much. I don't know if there's time for questions, but you're welcome to ask me anything, not about Kafka, Kinesis, or...
First
yeah.
of all, stunning slides.
Thanks.
On the architecture 3.0,
Yeah.
we can deploy REST services nicely, we can scale them out, and we can
Yeah.
cover them everything. And you can test them, and you can do health checks.
Okay.
And this architecture 4, like, you still need to do that.
Yeah.
Like, how do you deploy it, I guess?
You must do those things still, I think. I don't know. I'm not sure, but I mean, so one of the interesting things from architecture 3.0 to 4.0 is you can think about dropping stuff like load balancers, service discovery. Those things are no longer required. It's not like I've got this request that needs to find its mate somewhere in this mesh of things. With streaming, it's like the process is already there. It's bound to, I just got to drop it on the right stream. It's already distributed, if that makes sense. So things like service discovery, circuit breaking maybe is still a requirement. There's no real requirement for load balancing because streams themselves are, by their very nature, load balanced. Do you know what I mean? But I mean, it's not to say that we must throw away all those good things. Like, stream processes still work brilliantly on Kubernetes with health checks and all that kind of stuff. Because when they crash, they do crash, right? If they read a record that they're like unhappy with and they decide to crash, they crash. And so you still need to be monitoring them with all the same kinds of methods that you used to before. You know what I mean? Yeah. So we quite often use Kubernetes. Like, Kubernetes to host your stream processes is brilliant. Yeah.